In this session, we'll look at some further differentiation. We'll be looking at some second derivatives, and we'll jump straight into some questions. So this first one says, an equation is defined by y is equal to x squared over x plus 1. So this is x squared over x plus 1, and they want us to find the second derivative d2y by dx squared. Now obviously, before we can find the second derivative, we must find the first derivative dy by dx. So let's proceed to doing that. So we have y equals x squared over x plus 1. We should be able to recognize this as a fraction, of course, in the form u over v. So we can say, let's write it as y equals x squared over x plus 1, which of course is the same thing as u over v. And for this, we're going to have to apply the quotient rule of differentiation. So what is the quotient rule of differentiation? Let me just drag your memory a little bit. We say that if y is equal to u over v, then this means that where of course u and v are functions of x, then dv by dx is equal to v du by dx minus u dv by dx all over v squared. So this of course is v du by dx minus u dv by dx all over v squared. So if we say that let u be equal to x squared, which therefore means that du by dx is equal to 2x. Secondly, we say that v is equal to x plus 1, which therefore means that dv by dx is equal to 1. And of course, by the quotient rule, say that dy by dx is equal to v du by dx minus u dv by dx all over v squared. Right, so we continue. So therefore we get that dy by dx is equal to, so of course let's just highlight them. So we have u is equal to x squared, du dx is equal to that, and v is equal to x plus 1, and so on. Right? So what we're looking for here now is v du by dx. So this is x plus 1 times 2x minus u, which is x squared, times dv by dx, which is 1. And this is all over x plus 1 squared. Alright, we can proceed to simplify. So this basically becomes, expand the brackets, 2x times x, that gives us 2x squared. Then 2x times, so let me just write this better. So this is 2x squared, then you have 2x times plus 1 is plus 2x. And from that we're subtracting x squared, that is all over x plus 1 all squared. Now at this stage we don't need to expand the brackets in the denominator, we could leave it as it is. So let's just leave that as it is and proceed to simplifying the numerator. Alright? So this is going to give us 2x squared minus x squared is x squared. So this is x squared plus 2x divided by x plus 1 all squared. So that is dy by dx. But what are we required to find? We're required to find d2y by dx squared, the second derivative. So we can write that dy by dx is equal to x squared plus 2x over x plus 1 squared. Again, this is of the form u over v. And of course, we're going to have to apply the quotient rule once again. So we can say, let u equals x squared plus 2x, which therefore means that du by dx is equal to 2x plus 2. Similarly, we say let v equals x plus 1 squared, which therefore means that dv by dx equals, now this basically is a composite function, so we're going to bring the 2 down, multiply by it, reduce the power by 1, then multiply by the derivative of what is inside the brackets. So let's put that into practice. So bring the 2 down, multiply x plus 1, the power reduces by 1, so 2 minus 1, that's basically 1. Then of course we multiply by the derivative of what is inside the brackets. Inside the brackets you have x plus 1, and when you differentiate x plus 1 you simply get 1. So this is simply equal to 2x plus 2. Right? So this is equal to 2x plus 2. Now we can say that according to the quotient rule, dv, in this case we're looking for d2y by dx squared because the second derivative. So we can basically say that d2y by dx squared is equal to v du by dx minus u dv by dx all over v squared, and we can continue. And so what we get is this: d2y by dx squared is equal to, in this case v of course is x plus 1 all squared, so this is x plus 1 all squared, times du by dx, which of course is 2x plus 2. Then of course you're going to subtract minus u, which is x squared plus 2x, times dv by dx, which is 2x plus 2, and this is all over v squared. Now v is equal to x plus 1 squared, so therefore v squared is going to be x plus 1 to the power 4. Right? Now let's see how best we can, let's see if we can actually simplify this. Can we simplify this? We probably can, but do we need to? We probably don't, but let's try see how far we can actually simplify this. So basically the first two terms, this is going to be like yeah, this is going to be, if you factor the 2 from this, we get 2 times basically x plus 1 squared times x plus 1, right? And this is going to give us a 2 down here again, x plus 1 times x squared plus 2x, and this is all over x plus 1 to the power 4, right? So basically we can factor out, we could leave it, but anyways, one last step. So this is x plus 1 squared, this is x plus 1, so that's going to give us 2 open bracket x plus 1 cubed, and this is minus 2 times x plus 1 times x squared plus 2x, and this is all over x plus 1 to the 4th. So there's no requirement to actually simplify it any further, so just leave it as that. So that is the second derivative of y equals x squared over x plus 1. Now let's look at another example. This one says, given that y equals x over x plus 1, show that d2y by dx squared is equal to 2 times y minus 1 all over x plus 1 squared. So they gave us the function y expressed explicit in terms of x, and we're asked to show that the second derivative d2y by dx squared is equal to this, which is 2 bracket y minus 1 times x plus 1 all squared. Again, we're going to have to apply the quotient rule. So we can say u equals x, which means that du by dx is equal to 1. Also, v is equal to x plus 1, which means that dv by dx is also equal to 1. By the quotient rule, we can say that dy by dx is equal to v times du by dx minus u dv by dx all over v squared. And so this is going to give us v, which is x plus 1, times du by dx, which is 1, minus u, which is x, times dv by dx, which is also 1, all over x plus 1 squared. So this is simply equal to x plus 1 minus x over x plus 1 squared. The x's cancel, and so we get that dy by dx is equal to 1 over x plus 1 squared. So dy by dx is equal to 1 over x plus 1 squared. Now, we're not finished because obviously we have to find the second derivative. So we have to find the second derivative, and what we'll do is that we will still treat this as a quotient. We'll treat this as a quotient, u over v, and of course we'll apply the quotient rule. So let's do that. So we say that u is equal to 1, which means that du by dx is equal to 0. Also we say that v is equal to x plus 1 squared, which means that dv by dx is equal to 2 times x plus 1 times the derivative of what is inside the brackets, x plus 1, which is just 1. So this of course is equal to 2x plus 2. And again, by the quotient rule, this time however, we're finding d2y by dx squared. So d2y by dx squared by the quotient rule is v du by dx minus u dv by dx all over v squared. Right? So this is going to give us, squeeze it there. So v is of course x plus 1 squared. So this is x plus 1 squared. And du by dx of course is equal to 0. Then minus u, which is 1, times dv by dx, which is 2x plus 2. And this is all over v squared. Now v is equal to x plus 1 squared, which therefore means that v squared is equal to x plus 1 to the 4th. So we can try to simplify that and see what we get. So we get d2y by dx squared is equal to, this first term of course is 0, this is 0, and we basically have minus 2x minus 2 all over x plus 1 to the power 4. Right? Now, what happens here? So this is basically going to give us, if we factor out a minus 2, then this becomes x plus 1 over x plus 1 to the power 4. But we are told to show that it is in the form 2 times y minus 1 over x plus 1 all squared. So basically we can simplify this. We can simplify this a little. So this is going to give us minus 2 over, minus 2 over x plus 1 cubed. Because of course x plus 1 will go into x plus 1 to the 4th, leaving x plus 1 cubed. Now we can also write this as minus 2 over x plus 1 times x plus 1 squared. Right? So this is equal to minus 2 over x minus 1 times x plus 1 squared. We can write this as this, minus 2 over x plus 1 all over x plus 1 squared. And of course we try to see if this part, if we compare to what we're supposed to get, which is 2 times y minus 1. Right? Now let's look at what that gives us. We have y is equal to x over x plus 1. So y is equal to x over x plus 1. So y minus 1 would be equal to x over x plus 1 minus, now because this is a fraction with the denominator x plus 1, 1 would be the same thing as x plus 1 over x plus 1. So we're subtracting that. And so that gives us x minus 1 over x plus 1. These cancel, and so this gives us minus 1 over x plus 1. And so therefore if y minus 1 is equal to minus 1 over x plus 1, then it simply means that minus 2 over x plus 1 is actually equal to 2 times y minus 1. So we have to go back to the right hand side of what we wanted to show, the numerator 2 times y minus 1, to show that this right here, minus 2 over x plus 1, is actually equivalent to 2 times y minus 1. And so we've basically proven what we set out to prove. So therefore, by virtue of that, this is proven that given that y equals x over x plus 1, then d2y by dx squared is equal to 2 times y minus 1 all over x plus 1 squared. Right? That is what that one there. So let's look at another example. This one says, show that y equals 2x plus 5 times e to the 3x satisfies the equation. So satisfies the equation d2y by dx squared minus 6 dy by dx plus 9y equals 0. So we're given this equation y equals 2x plus 5 times e to the 3x, and we're asked to show that it satisfies the equation d2y by dx squared minus 6 dy by dx plus 9y equals 0. So let's proceed. Obviously, in this here we have a second derivative as well as a first derivative, so we have to proceed to find the first derivative and then the second derivative, right? So let's do that. Now this basically is a product, so we can write this as, well, we can say this is our u and this is our v, and of course the product rule of differentiation. If y is equal to uv, then this means that dy by dx is equal to u times dv by dx plus v times du by dx. So this basically is our product rule, which of course we need to apply in this particular problem, right? So let's proceed. We can see that dy by dx is equal to, so it is 2x plus 5 times the derivative of e to the 3x. Now e to the 3x is a composite exponential function, and to differentiate the function, you differentiate the the power, and you multiply by that derivative. So the power here is 3x. When you differentiate 3x, you get 3. So therefore that derivative is simply going to be equal to 3e to the 3x. So we differentiate the power and we multiply by it and we keep the function, right? So the derivative of 3e to the 3x is, or the derivative rather of e to the 3x is 3e to the 3x. So this is just the first part. This is u times dv by dx. Then there's going to be plus v, which is e to the 3x, times du by dx, which is simply 2. When you differentiate 2x plus 5 with respect to x, you simply get 2. And so what we get here is this, that dy by dx is equal to 3e to the 3x times 2x plus 5 plus 2e to the 3x. Now what we can do is to simplify this to get a single term. So we can factor out the e to the 3x, which is going to give us 3 times 2x plus 5 plus 2. And we expand and simplify the bracketed terms. So this is going to give us e to the 3x times, this is 6x plus 15, and 15 plus 2, that is 17. So e to the 3x times 6x plus 17. Right? That is what dy by dx is. So let's write that down now because I have to differentiate a second time. Right? So we say that now dy by dx is equal to e to the 3x times 6x plus 17. And once again, we're going to have to apply the product rule of differentiation. So we say now that d2y by dx squared is equal to the first, which is e to the 3x, times the derivative of the second. When you differentiate 6x plus 17, we get 6. Right? Then we say plus the second, which is 6x plus 17, times the derivative of e to the 3x, which of course we established from the first part is 3 e to the 3x. And of course, we try to simplify this again. So this becomes 6e to the 3x plus 3, open bracket, 6x plus 17 times e to the 3x. So here we can actually factor out e to the 3x. We can actually factor out 3e to the 3x. So this becomes 3e to the 3x. This is going to leave us with 2 plus 6x plus 17. With the same thing as 3e to the 3x times 6x plus 19. So that is our second derivative, but we're not finished. We're asked to show that it satisfies this equation. So now we basically have to substitute those into the equation on the left hand side at least and see if it actually equates, gives 0. So what we want to find is this: d2y by dx squared minus 6 dy by dx plus 9y equals. So d2y by dx squared is of course this. So that will go there. Dy by dx of course is this. And of course this is y that we had from before. So let's do our substitution and see what that gives us. So d2y by dx squared, this is equal to 3e to the 3x times 6x plus 19. Then it's going to be minus 6 times dy by dx, which is this. This is minus 6 e to the 3x times 6x plus 17. And then lastly, we have now plus 9. So let me write it here. Plus 9 e to the 3x times 2x plus 5. Right? So let's try and simplify the numerator and see what that gives us. So we're going to factor out e to the 3x from the right hand side. So we get e to the 3x. So now we're going to left in the first bracket we have 3 times 6x plus 19. In the second bracket we're going to have minus 6 times 6x plus 17. And in the third we're going to get plus 9 times 2x plus 5. And if this is to be proven, the numerator most likely should reduce to 0. So let's check that. We get e to the 3x bracket. Now 3 6's, that's 18x plus 19. 19 times 3, that is 57. Then minus 6 times 6, that is 36. This is minus 36x. Then 6 times 17, 6 10 60, 6 7 42, that is 102. This is minus 102. Then you have plus 9 2's are 18x, and then 9 times 5, that is plus 45. Now let's see what happens with these numbers inside the square brackets. We have e to the 3x, and essentially we have 18x plus 18x minus 36x. So clearly those will be equal to 0. Then now we have plus 57 plus 45 minus 102. Right? So basically we get e to the 3x times, this is 36x minus 36x plus 102 minus 102, which of course is simply equal to e to the 3x times 0, which is equal to 0. So this therefore has been proven. We've proven that given y equals 2x plus 5 times e to the 3x, then in fact d2y by dx squared minus 6dy by dx plus 9y is indeed equal to 0. Alright, so we've proven that one. Now let's go on to do another. Alright, let's go on to another. This one says, given that y equals ae to the minus 2x plus b e to the x, show that d2y by dx squared plus dy by dx minus 2y equals 0. So let me read the problem again, make sure I have it properly correct. Given that y equals ae to the minus 2x plus be to the x, show that d2y by dx squared plus dy by dx minus 2y equals 0. Right, so I copied it down properly. So let's proceed. So obviously we have to find the first derivative, then we have to find the second derivative, substitute all of them into this equation and see if they actually equate to 0. So we have y equals ae to the minus 2x plus be to the x rather. So say that dy by dx equals, now a and b are multiplying constants, so we keep them, so it's going to become a bracket. Again, we're differentiating an exponential composite exponential function, and so typically we can say that, for instance, d by dx of e to some function f of x is simply equal to f prime of x e to the f of x. So we basically keep the exponential function, the composite exponential function, and multiply by the derivative of the exponent, right? So therefore what this is going to give us is this. When you differentiate minus 2x, we get minus 2, simply minus 2e to the minus 2x. Then we have plus, well, e to the x, the derivative is just e to the x, so that is just remains as b e to the x. Now that is the second derivative. So over we can just, let's leave it as that for now. And then now we can say that d2y by dx squared is equal to, we can still keep our multiplying constant a outside. And then now we're going to multiply, and of course our minus 2 stays as well. So once again, the minus 2 is a multiplying constant, so we can keep that. But when we differentiate negative 2x, we're going to get negative 2, which we have to multiply by again. So let's put it here. So we have minus 2 times minus 2, and then e to the negative 2x. And of course, be to the x remains as before, because b is a multiplying constant, and the derivative of e to the x is simply e to the x. So basically what this gives us is that d2y by dx squared is equal to, so minus 2 times minus 2, that is 4. This is 4a e to the minus 2x plus b e to the x. And of course we can check this equation now. We can substitute the values into that equation and see if it's actually equal to 0. So we can say that d2y by dx squared plus dy by dx minus 2y equals, so d2y by dx squared is this right here. dy by dx is of course this, where we can actually just put minus 2a in front there, and of course that is our y. So this is going to give us 4a e to the negative 2x plus b e to the x. Then now for dy by dx, that gives us minus 2a e to the minus 2x plus b e to the x. And then minus 2y, that's going to be minus 2a e to the minus 2x. And of course minus 2b e to the x, right? So we see that essentially what we have is this. For the a e to the x terms, we have 4a e to the minus 2x rather. We have 4a e to the minus 2x. Then of course these two, we have minus 2a e to the minus 2x and minus 2a e to the minus 2x. So those two combine to give us minus 4a e to the minus 2x, right? Similarly, we have b e to the 2x plus b e to the 2x, and those combine to give plus 2b e to the x. And then now we have to subtract 2b e to the x. So clearly, these two cancel, and these two cancel, so the result is simply equal to 0. And once again, we've proven the desired result. Right? So in this session, we're able to look at second derivatives, and we're able to differentiate combinations of different functions, exponential regular functions of x, and we're able to prove a given result by finding the first derivatives and then the second derivatives.